Okay, we're back, and this is Chapter 6, Basic Circuits. Some we've seen already, a couple more here. Useful as it relates to ASIC layout, perhaps, and as you know, a big chunk of the ASIC market is not an FPGA. Just as a side note, FPGAs are approximately 10% of the ASIC market, but this section does help us lead towards some FPGA circuits. So basically this section is some low-level logic circuits for VLSI. It's perhaps more useful as an overview. We'll take a look at some transistor level schematics, some very basic layouts showing the basic layers, some standard CMOS logic. Basically we'll look at NAND and NOR. Illustrations are somewhat simplified, but detailing the primary layer information, and sort of, we'll be able to see where we get our load capacitances from and things of that nature. The current processes are extremely complex with many more layers than those that are shown here. So we'll look at a few standard gates, and these will be NAND, NOR, XOR, and flip-flops in this chapter. But when you're laying out a large logic circuit, it's more desirable to have a circuit hierarchy. A microprocessor, for example, is not laid out as a mass of individual transistors. It may have been at one time, but that would have been in the early days of maybe the 4004 from Intel or something. A more intuitive approach would be to design a few gates, such as NAND, NOR, flip-flops, and then from there higher level structures like registers and arithmetic logic units are created. So this is pretty much a bottom-up approach. It is a natural way to solving a more difficult problem, certainly not the only one, and it's usually somewhat evolutionary. I think a good rule of thumb is on a maximum product change, something on the order of 10% is sort of what is considered reasonable. If you have much more change than that, it's going to be more difficult to test and manufacture and get right. And so as a consequence, typically it's that kind of number on a product change. So we're pretty much interested in the reuse of standard circuits and gates to build larger cells. And once these larger modules or mega cells are created, the next design would then use these structures in a more top-down approach. So the modern terminology for that might be the library of parameterized modules, so LPM. And the emphasis here is not to reinvent the wheel. With higher level, at an even higher level, it might be called IP or IP cores. So these stand for intellectual property cores. And as in-class assignment here, I provide two examples of a core or a library parameterized module. And if you've been doing the Altera labs, that shouldn't be too difficult at this point in time. So here's a basic circuit. It's our NAND gate. We're going to look at a NAND gate with 2, 3, and 4 inputs at the transistor level. So these are basically just showing us the arrangement of the transistors, and it's very straightforward. For the NAND gate, the PFETs are all in parallel. All their sources are connected to VDD. All their drains are connected to Vout. The NFETs are arranged in series, and the bottom NFET, the source is connected to ground. The top NFET, the drain, will be connected to Vout. So here's a simple representation, transistor level schematic of a 2-input NAND gate, 3-input NAND gate, and 4-input NAND gate. And probably quite reasonable that you'd expect to recognize a pattern. And this is also the basic structure that you might find in a NAND flash device. So here's an example of a layout. It's only a few layers that are shown here that are illustrated on the right-hand side. And as you can sort of see, we have two P-type devices which are in parallel, so their drains are connected together and connected to Vout, and two N-type transistors which are in series. So what you might ask yourself, based on things that we saw before, what might be the load capacitance for this gate? Well, we can certainly estimate it, how we were doing it before. We were looking at this contributing to the load capacitance. This is part of the output, and it's the drains of the two PFET devices. There's the drain of an NFET device, and it'll contribute to the capacitance. And depending on the input pattern, this region down here could also hold some charge that we may have to discharge if we were pulling it down. So it could also contribute to the load capacitance. The other thing to note is sort of the widths of these devices and their geometries, and they're in this fashion such that we'll basically get an equal rise and fall time on the worst case type of scenario. So the worst case pull up would be through one PFET, and of course the worst case pull down, I guess, would be through both of these N-type transistors would have to be on. So the cell has a few notable features. The VDD and ground form a bar that extends across the top and bottom, and for any given cell these would typically all be at the same distance apart, so that you'd be able to butt those cells together, and then you'd form ground and VDD across a number of cells which are in a row. The size and the line spacing would be standardized, and that would be associated with the cells that are in that standard library. The input A and B are connected to gates, so these are the gate inputs, the MOS devices, using some kind of a contact hole, so that was denoted CA previously. In this case, it's between the first metal level M1 and the polysilicon strip, which would form the gate of the PFET and NFET. So polysilicon is probably still a carryover, but it would be, a polysilicide of some type. Again, the two PFETs are butted at their drain. That's to save space and to aid in performance. So basically, that was a designer that pushed those together as closely as they could without violating design rules. And there's similar connection strategies for the NFET. The source of one becomes the drain of the other. Other things to note is that the PFETs are in the same well, so they share a well, and that would likely be tied to VDD. Likewise, the P well, where the NFET tub, if you like, where the NFET devices are, is also tied to ground. More recent CMOS technologies, the wells and substrates can be biased. If you remember, very early on, we had 4 terminal devices, and one of those was a body terminal, so it doesn't have to be tied to VDD or ground, but could be perhaps, in the case of the N-type transistor, a little lower than ground, and that gives you a dynamic threshold voltage. So there's some advantages to that type of design. For example, being able to design for both high speed and low power on the same chip, and we saw some examples of that early on, and probably not touch much upon that now, other than to realize it's another parameter that can be optimized. Extending the basic circuit to a NOR gate, well, it's the very same idea. In the pull-down section, we basically have an OR function, and since it's in a CMOS configuration, it's going to be a NOR gate. So these two transistors are in parallel. These two pull-up devices are in series, and you extend that quite easily from 2 to 3 input, 2 to 4 input. Here's a layout for the NOR gate, and again, now we have the 2 P-type transistors, which are in series, and the 2 N-type transistors, which are in parallel, and then they share a common drain. And again, Vout would be here. So again, you could ask yourself, what would be the load capacitance if you're looking at this node here, and it would be all the metal capacitance associated with this diffusion capacitance area and perimeter, this diffusion here, area and perimeter as well. In addition to that, when you calculate the load capacitance, you typically think of talking to a similar gate. So you may be driving something like this input here, where you'd have to account for these 2 gate capacitances. So the basic NOR gate, the PMOTs are connected in series, as we saw. The NFETs are connected in parallel, and that's basically opposite to the NAND gate. The schematic and layout, many similar or same features to the NAND gate, and one noticeable feature is the large PFETs in series. And these are larger, if you recall, to obtain equal rise and fall times, as we discussed in previous chapters, because one of the reasons for that is the mobility of holes is less than that of electrons. Another point to note is that layout is used for placing parts of the design relative to one another, and these have to sort of meet with the low-level physical design rules, so the size and shapes and distances between components will be minimized, and yet allow the device still to be fabricated. So it would be according to the design rules of given technology. The actual cell layouts usually attempt to minimize area and definitely use very clever orientations and connections of transistors to achieve this. And it's usually on some type of Manhattan type of structure. You noticed before, all of the wiring was either horizontal or vertical. And at this point, I'll take a break.